Hello and welcome to your parallel test review. Best way to use this is to check your answers. You're going to have to some extent, do a little bit of searching and kind of scroll through the problems that you want to see worked out. I'll do the best job I can to kind of go through these carefully. I'm going to reference you to certain reference tables and pages in your note packet as well. So question number 1, compound classified as an electrolyte. This relates to page 5 and 6 in your note packet. Choices 1 and 2 are both sugars. They are same side of the staircase. Electrolytes have to be opposite sides of the staircase. The only compound that is not opposite sides of the staircase that could be an electrolyte is a Cu group. So you're going to get rid of the first two choices. They're same side of the staircase. They're sugars. They're not electrolytes. Choice 3 is also same side of the staircase. It ends in OH, which makes it a little bit confusing, but this is considered an alcohol, which is also a non-electrolyte. CaOH2 is a base. Bases are electrolytes. Question number 2 is just an Arrhenius base definition question. Anytime you have an Arrhenius bases yield OH as the only negative ion in solution, and that was in our notes on pages 1 through 3. When an Arrhenius acid dissolves in water, this is kind of the opposite of the question before it, so we're looking now at the acid definition. The acid definition is that we are going to get H plus ions in solution, and that's also a definitional question from page 1 to 3 as well. So you can access the same pages. We had a nice table that we did that kind of summarized that. Which compound is a non-electrolyte? Remember, a non-electrolyte will not conduct, which means it's not going to dissociate. NH3 can be a little bit confusing because it does look like it's going to be same side of the staircase, and it sort of is. What I recommend doing, however, when you're identifying electrolytes, check first if they're an acid or a base. So while looking at table K and L, NH3 is a base. Bases are electrolytes. Next, you're going to look at CH3OH. That is same side of the staircase, and that is an alcohol. So I'm not going to rule that one out. That's going to be our non-electrolyte. Just to show you the other two, KBr is opposite sides of the staircase. That's a salt. An ionic compound. Ionic compounds are electrolytes. And HCl is an acid. And you can find more information about this on page 5 and 6. So classifying compounds, again, is going to be extremely important. Number 5, the hydrogen ion in aqueous solution. What could actually happen with this is a hydrogen ion, sticks itself onto H2O and yields something called the hydronium ion, which is H3O+. And that's also given on reference table E. It's definitional as well. We talked about that on page 2 of your notes. What are the relative ion concentrations in an acid solution? Acid should have an excess of H+. So we want to have more H+, less OH-. Choice 2 would describe a base. Choice 3 would describe a pH of 7. And there's not an example of a solution that truly doesn't have H+ and OH- ions. Acid solutions have OH- ions. They just don't have as many of them. And you can find this on page 7 in your notes. Question number 7. A student is given 4 unknown solutions, checked each one of them for conductivity, and tested them with phenolphthalein. The results are shown in the data table below. So we want to figure out which one is going to be 0.1 molar NaOH. So with 0.1 molar NaOH, you could go ahead and calculate the pH of this if you wanted to. For questions that we're going to be doing, if they're telling you got NaOH, we're talking about a basic solution. So we need to determine which one of these is basic. If you wanted to calculate your pH, you do pOH first. Your pOH would actually be 1, which gives you a pH equal to 13. Again, basic. So in order to be a base, we do know we have to have conductivity. So poor conductivity is going to rule out B and D. So now we're looking at A and C. So now we want to figure out, will phenolphthalein be colorless or pink? So we're going to go over to reference table M. And a basic solution, especially this one with a really high pH, in phenolphthalein, we're talking pH of 13, so something high over here, we're going to have pink as the color of that solution. So we're going to go back over here, and our pink solution would be C. And again, that is a combination of table M and identifying a base as well, so you're also kind of looking at table K and L. Question number 8, how are HNO3 and CH3OH AQ similar? We're going to go to tables K and M for this, or I'm sorry, yeah, table K and M. So table K has our common acids on it. HNO3 is an acid, and CH3COOH is an acid as well. So the first thing that we're able to do on that question is we're able to say, hey, these guys are going to be Arrhenius acids, so we're just going to get rid of our base choices. Should we turn litmus red, or should we turn litmus blue is the next question. When they talk about blue litmus turning red or red litmus turning blue, the color that the litmus is beforehand doesn't matter. So when we have litmus turning red, litmus is going to turn red in a lower pH solution, below 4.5. pH of below 4.5 is going to be an acid. So my solution should turn litmus red. So you also have to know low pH is an acid and be able to relate that to table M. Given the reaction, NH3 plus HCl makes NH4Cl. What's going to happen here, this H is actually, well, this H and the Cl are actually both sticking themselves onto ammonia. The formula that we looked at before that sort of, or the reaction that we looked at before, looks a little bit different than this. We have that one H that goes over there, so we end up with NH4 plus and OH minus ions. So what's actually occurring here is you can say that ammonia, which is this, acts as a base because it accepts hydroxide, accepts hydrogen ions. So definitionally speaking, we want to accept hydrogen ions. When we are accepting hydrogen ions, again, this is very definitional. So this comes from that alternative theory, which is discussed on page 4 in your packet. Which statement correctly describes a solution with a pH of 9? pH of 9, you need to know, is basic. So what this means is a basic solution should have a high concentration of OH minus ions. So then it does of H3O plus ions. That's another thing that we did in the notes that you can, you have a nice table describing it on page 7. So we want to have a higher concentration of OH minus, so it's not going to be choice 1. Could be choice 2, higher concentration of OH minus. We do not want it to be choice 3. Could be choice 4. Now we also have to go to table M. And we want to find out, should our litmus turn blue, or should our should our methyl orange turn red? So if we look up litmus turning blue, litmus turns blue at a pH over 8.3, so that could very much be our answer. We'll check the methyl orange when we're here. Methyl orange turns red in a lower pH range, a pH of below 3. So if methyl orange is red, it's definitely indicating an acidic solution. So this solution, if it's turning litmus blue, it has to be basic, so therefore choice 2 is going to be our answer. Number 11, which pH change represents a 100-fold increase in the concentration of hydronium? Now remember, a 100-fold change means we have 2 pH units of change. And we're talking about increasing our H3O plus, which means we're getting more acidic. Therefore, pH should go down. So we want to say, okay, we need a twofold change, and we should be going down 2 units. So 5 to 7 is twofold, but it's up. This is only one unit. 3 to 1. It's going to be our answer. That's only changing by 1 unit. Which pH indicates a basic solution? This is very straight up definitional, knowledge based. Anything that is a pH greater than 7 is going to be a basic solution. Number 13, a substance is classified as an electrolyte because this is definitional. Electrolytes must conduct in aqueous solution. So anything that's an acid, base, or salt is going to be conducting. It has to dissociate, give you mobile charged particles. Which aqueous solution is going to be the best conductor of electrical current? So we have to identify first which of these will conduct. This is booze. So is this. Electrolytes are not booze, or booze are not electrolytes. You booze, you lose. So we got 0.01 molar KOH and 0.1 molar KOH. The way we're deciding between those is based on concentration. 0.1 molar KOH has a higher concentration, therefore it will be more conductive because it has more ions in solution. Highest concentration of H3O plus ions is going to be the lowest pH because we're talking about an acid here. So this is going to be a pH of 1. Number 16, which 0.1 molar solution has the lowest pH? So for lowest pH, we're looking for something that is acidic. NaOH, we can say is a base, so that's probably not going to be our answer. Alcohol and salts are going to have a pH equal to 7. So NaCl is also, it's just a salt, it's not an acid or base, pH equal to 7. So we can cross out both of those, they're the same answer. HCl is an acid, that's going to have our lowest pH. And that was a combination of things from page 6 and also using tables K and L to identify acids, bases, and things that aren't either one. The hydronium ion concentration of a solution is 1 times 10 to the negative 4. So this really just means this, which is the same thing as this, is this. That is your pH, as long as that's a 1. We did some calculations in class where that wasn't a 1. Everything you're doing on this test is going to have a 1 there. So this solution is going to have a pH of 4. So I'm crossing out this guy, crossing out this guy. And because we have a pH of 4, we have a pH below 7, is acidic. When our pH equals 7, we have a relationship where our H pluses and OH minuses have canceled each other out. This is called neutralization. And you have a nice table again in your notes that talks about the relationship between these. I think it might have been on page 7. Somewhere around there talks about that, relationship in an acid, more H plus, and a base, more OH minus. When they're neutral, you meet in the middle. Which solution will turn phenolphthalein pink? So in order to turn phenolphthalein pink, we need to have a pH that's at the very least 8. Okay, so this question is saying to us, the very least, our pH is going to be 8. This is an alcohol. Alcohols are neutral, their pH is 7. This is an acid. An acid has a pH below 7. This is an acid. pH below 7. NaOH is a base. pH will be above 7, probably likely above 8 as well. Which solution is classified as Arrhenius base? This is just one where you're looking at tables K and L. You're going through and deciding if something's an acid or a base. This guy's an acid, base. Both of these are actually what we would classify as salts. They are opposite sides of the staircase. They would actually dissociate. They will make mobile charged particles and be electrolytes, but choice 2 is our Arrhenius base. Number 21 is the H3O plus concentration of a solution increases, the OH minus concentration decreases. The pH of the solution, what? So we're getting more we're getting more hydronium whenever we have an increase in H3O plus. We're getting more acidic, therefore we are dropping pH. So what is going to happen here? The pH of this solution is going to decrease. Number 22, according to an alternate theory of acids and bases, this is definitional, so this was on pages 2 through 4 in your notes. An acid is any species that is going to donate protons. This means the same thing as giving away H plus ions. Keep in mind that we use these terms pretty interchangeably in this unit. Number 23. If we go to, we have this laboratory data. If we go toward, sorry about that. If we want each of these to appear yellow. So this is going to be yellow below 6.2. This is going to be yellow above 2.8. And this is going to be yellow above 4.4. So, choice 1, 1.9. Thymol blue will not be yellow. So we're going to go ahead and say it can't be choice 1. Choice 2, 2.9, that's not going to work. It's not above 4.4, which it would need to be for methyl orange. 4.7 is below 6.2. It's above 2.8. It's above 4.4. So that's going to be our answer. The reason that 8.7 won't work is it won't work for bromethymol blue. Given this reaction, we want to know which one is a Bronsted-Lowry acid. Bronsted-Lowry is referring to that alternative theory, which is usually what you're going to hear for that. Again, that goes back to the beginning of the unit, pages 3 and 4. In order to be considered a Bronsted-Lowry or alternative theory acid, we have an acid that is donating protons or donating H pluses. What's happening if you look at this reaction is this guy is giving an H plus to that guy. So HCl is our acid because it donated protons. Which of the following represents neutralization? Whenever you neutralize something, you always remember write a water and a salt, okay? So it's an acid plus base makes water plus salt. We covered this on page 11 if you need to look back on it. So choice 1, we have magnesium and hydrochloric acid. We don't have a base there. We only have an acid. Choice 2, HCl is an acid. KOH is a base. Over here we have a water and we have a salt. The other two, we just don't have proper acids, bases, salt, and water formation. Usually it's best to look for a water in your product, then double check that you have an acid, a base, and a salt forming. Number 26 is a calculation. So it's the titration calculation. We have 50 milliliters of 1 molar NaOH that is needed to exactly neutralize 10 milliliters of a hydrochloric acid solution. We want to find the molarity of the hydrochloric acid. So we're looking for the molarity of the acid. We're multiplying that by the volume of the acid, which is 10. And we have a 1 molar basic solution that we're using 50 milliliters of. If you were to reverse the sides of these, it's not a problem as long as that 10 milliliters is grouped with your variable and the 1 molar and the 50 milliliter go together. And that gives us a 5 molar solution. Which compound reacts with an acid to form a salt and water? I'm going to draw your attention right back up here. What reacts with an acid is a base. So we have to look through these, determine which one's a base. This is really a covalently bonded compound. It is not an acid or a base. We got a Cu group here. It's an acid. KCl is not an acid or a base. It's a salt. Oops. And KOH is a base. Again, tables K and L will help you with that identification if you're still struggling a little bit with that. In performing a titration, a student adds 3 drops of phenolphthalein to a flask containing 25.00 milliliters of H2SO4. So this is going to be our molarity of our acid. Using a burette, the student adds 0.25 molar NaOH to the flask until 1 drop causes the indicator to stay light pink, so just like what we did in class. And we are determining that we use 20 milliliters of that base, the NaOH, in the titration. So first you're going to go ahead and write your neutralization. We always make a water, then we got to make a salt. Remember, the OH here and these H's, both of them are going to end up in water. We haven't balanced that out yet, but they're going to end up there. So we got Na plus and SO4 2 minus left over, which gives us Na2 SO4. And you're going to go ahead and make a balancing table, which I'm not going to walk through here on here because you've done it a million times, which will cause you to balance this. You need a 2 here, and you need a 2 here. Next thing we're going to do is we're going to find the molarity of the H2SO4 that was used in this titration. So we're using our titration formula. Again, this is from table T, also page 12 through 13 in your notes. Now, we do have to keep one thing in mind here, and that's the fact that this is a diprotic acid. There's a 2 in that H2SO4. So we are going to actually need to keep that in mind when we do this calculation. So we're going to plug in. We don't know our Ma. That's what we want to solve for. We're going to multiply that by 25 milliliters. And then our Mb times our Vb. Now, NaOH only has 1 OH in it, so we don't need to change anything about that at all. Because of this 2, we need to throw a 2 on our acid side. So what this is going to do for us, this side will be Ma times 50 equals 5. To get that by itself, we got to multiply or divide each side by 50, which is going to give us an Ma of 0.1 molar. So it's very common to incorrectly get 0.2 molar on that because of forgetting to bring down your 2 from up above. So make sure that if you got 0.1 for that, you understand why you have to bring that 2 down and why you end up with 2 there. This graph has a lot to do with pH and interpreting pH and how it relates to hydronium ion concentration. So hydronium ion concentration for lemon juice, you're finding lemon juice right here, reading down to this axis. You can write this a number of ways. You can actually get away with 10 to the negative 2, 1 times 10 to the negative 2, which can also be written as 0.01, and all of those come out in molar, although they do give you the M, so you don't need to worry about that. Bromethymol blue in a solution of seawater. So seawater has a pH of 8. We're going to go back to our reference tables. Bromethymol blue, if 8's over here, would be blue. According to the graph, what is approximately 100 times less acidic than tomato juice? 100 times, remember, is 2 pH units. Less acidic means our pH is going up. So we're going to find tomato juice, which is right here, and we're going to go up 2 units. So we're starting at a pH of around 4. We want to end up with a pH of around 6. The substance closest to that is milk. And we got one more titration here. No tricks on this one. Everything is, just 1, so everything will balance out really nicely, and you don't have to worry about bringing down a 2 in your calculation. In preparing to titrate an acid with a base, a student puts on goggles and an apron. The student uses a burette to dispense and measure the acid and base in the titration. In each of 2 trials, a 0.5 molar sodium hydroxide solution is added to a flask containing a volume of HCl, which is going to be our acid of unknown concentration, and we're using a phenolphthalein indicator. We want to write the chemical name for the acid used in this titration. It's going to be hydrochloric acid. And it is written as an acid with an AQ, so hydrogen chloride is wrong. Please write out hydrochloric acid. We're doing an MAVA equals MBVB calculation for 35 and 36. Using the volumes from trial 1, that's important, determine the molarity of the HCl solution. Show both numerical setup and the correct answer. So we want to use our trial 1 information right here. So our MA we do not know. Our volume of acid used is 10.22. Our MB is our standard that's right here. And we're multiplying it by our volume right there. And that should come out to give you 0.83 molar. Three bottles of liquid are labeled 1, 2, 3 and found in a storeroom. One of the liquids is known to be drain cleaner. Drain cleaners commonly contain KOH or NaOH. The pH of the liquids at 25 degrees Celsius was determined with a pH meter, and the results are shown below. This is important. KOH and NaOH are bases. So do you know what's in drain cleaner up till now? You might not. If you don't, they're telling you that, and then you're supposed to know, hey, those are bases. 37, explain how the pH results in this table enable a student to correctly conclude that bottle 3 contains drain cleaner. And this is because the pH of bottle 3 is above 7, which is the case in a basic solution. And you can go on to say, if you want, that's enough, but you can also say, and drain cleaner is basic or something like that. Yeah, that's a very complete answer as long as you talk about the pH, that's all that really matters. Explain in terms of pH values why Thymol Blue is not a suitable indicator to distinguish between bottles 1 and 2. So bottles 1 and 2 are at pHs of 3.8 and 7.0. And we want to assess Thymol Blue for this. So be careful to actually look at thymol, not bromethymol. So if we had some Thymol Blue, a pH of 3.8 is going to be down here, and a pH of 7.0 is going to be down here. Both of those solutions are going to be yellow. In other words, they're going to turn out the same color. And last but not least, soil pH can affect the development of plants. For example, hydrangea plants produce blue flowers when grown in acidic soil, but pink flowers when grown in basic soil. Evergreen plants can show a yellowing of foliage called chlorosis when grown in soil that is too basic. Acidic soil can be neutralized by being treated with calcium hydroxide, CaOH2, commonly called slake lime. Slake lime is slightly soluble in water. 39, compare the hydrogen ion concentrations of hydrogen ion concentration to the hydroxide ion concentration in soil when a hydrangea plant produces pink flowers. So we're going to find our hydrangea. I keep saying this wrong, where our hydrangea is going to be pink. So blue flowers, pink flowers. I kind of wrote over it. So pink flowers are going to occur when we have basic soil. So when a solution is basic, we should have more OH than H plus. So you want to say the concentration of OH minus will be greater. However you word that, or if you show it in symbols like I did, that's totally fine. An evergreen plant has yellowing foliage. The soil surrounding the plant has been tested with methyl orange and bromethymol blue. Both turn yellow in soil test. So you're going to go to your table M, and we're going to look at some possible pHs here. So methyl orange is going to be yellow. So if methyl orange is yellow, we're over here on this side, kind of the higher pH range. And we're also looking at bromethymol blue, which is going to be yellow as well. So this tells us our pH has to be at least probably 3.1 at the very lowest. So our pH has to be at least like maybe 4, but it could actually be anything kind of up to and around 6. So that really tells me my pH is somewhere hovering around that 4 to 6 range based on using table M. So in terms of pH value, chlorosis occurs when grown in soil that is too basic. So the pH really is just too low for this to be chlorosis. So since both of those are indicating yellow, this tells me my pH range is likely about 4 to 6, which is acidic. Chlorosis cannot, I mean, you could also say the soil is not basic. What you do have to make sure is that you mention pH. So you do want to mention specifically why in terms of numbers that is the case. Write an equation using symbols or words for the neutralization of ions in acidic soil by the ions released in slake lime and water. So a neutralization equation, a basic one, is always acid plus base makes water plus salt. The other thing that you can say is you can just talk about your ions, your H plus, and your OH minus, which would react together to make water. So really either of those would work for you.